charge carrier region and is attracted by the positive charge, and then this electron is moved to a contact, and this time on the front side, and we have the plus pole on the back side afterwards and the minus pole on the front side. And if this circuit is closed, we can contact something like a resistor, light, a battery, or something else which can consume this electricity from the cell. The voltage there generated is typical for silicon 0.7 volt, which comes from the properties of the material and from the density of the doping. So a typical photovoltaic cell has no load voltage of about 0.7 volts and is able to carry current if light is shining on the cell. So without light, we have any current, but few volts, maybe a few tens of volts, but the current comes only if we have light on the cell, on the panel afterwards. So, to make a PV power station, we don't need single cells, but a lot of cells connected in series to get a reasonable voltage, more than 0.6, of course. So in the first steps, a lot of PV cells are arranged in one module and are saved from rain and dirt and dust and corrosion and so on. It is put in a sandwich of some different materials. In this example, it is EVA, ethylene vinyl acetate, as a plastic layer, and protective glass on the front side protects against mechanical damage, and it's very transparent kind of glass which is used here. On the back side, we have also different plastic films to protect the module. In very modern installations, we have sometimes bifacial modules where light is able to come also from the back side. And in that case, we have to put a glass layer here on the back side too, and no Tedlar film. And everything is arranged in aluminum frame to make it possible to mount it on studs and stands. So it is, in the end, looks like this here, a module with a metallic frame, a small metallic frame. And these photos come from our new PV installation we have here in Flensburg. What you can see is our University of Applied Sciences here. It's a photo from the summer, of course, not from the winter. And because renewables are a big topic at our university, we have on one hand side a wind turbine with 250 kilowatts of power. It's quite old one. And on the rooftop of our so-called D building, we have an arrangement of a lot of PV modules which are newly installed this year. The first installation was 25 years ago, so we had to renew it and have switched this year to 30 identical half-cell modules. I will tell what it is, what it means, and we have now a total installed power of about 13 kilowatt peak, which means under best conditions we would expect about 13 kilowatts of power coming from the installation to the inverters and to our storage facilities. You can see also solar thermal modules here in the back, and something which is called a tracker, but that moves the panel in the best direction towards the sun the day over. So, but these are quite old techniques which are not used today. Modern modules often have so-called half cells, which means that one cell coming from the manufacturing process is cut in half. And you can see it here, that it is mainly half of a cell and another half of the cell. So some could wonder why industry does this, and the reason is to save losses in the connection process. Expect we would have here 54 cells connected in series in a total string. Then we would have losses all the string long through this module along this way. And if we make it in two half planes, so this is the middle symmetric line here, in two half planes, the lengths of the connections are only half on the one hand side, and on the other hand side, we have only half of the current. Half of the surface of the cell means half of the current. So the losses on one half plane here are cut by a factor of 8. The losses in the cabling and the connections are going on with the resistive, linearly with resistor, and quadratic with the current. And that means we have 1/8 losses, and in total we can cut it by a factor of 4. This losses in the connections, and this is so good that nearly every module today has this half cell arrangement. In total, it comes to 425 watt peak here, and we have an efficiency of about 22%. Low load voltage is nearly 40 volts with these 54 cells, and the maximum number of cells in modules are typically 72. So all modules have between 36 and 72 cells. So 54 or 60 is quite typical for modules today, and most modules have 400 watts and more, sometimes even more than 600. So there have been big differences. We have big difference to older modules from the past, where we have only a few hundred watts. We connect this to different arrangements. On left-hand side, you can see a grid inverter, and this is a hybrid inverter in the middle with a DC-connected battery storage facility.